Hello everyone. Today, let's discuss about the quick sort. Previously, we had discussed about the counting sort, I believe. So today we'll be discussing about the quick sort. Basically, quick sort is also a divide and conquer algorithm. So first we started with the merge sort, right? Merge sort was also divide and conquer algorithm. So quicksort is also a divide and conquer algorithm. So what it will do, let's see that one first in the steps. Basically, it select the pivot element. So it will select the pivot element, and what it will do, it will select the pivot element from the array and partition the other elements into the two sub array, and this will partition the other sub arrays into two this one subarrays, right? So this will be, so yeah, it will consider the pivot element, and then it will partition the other elements into the two subarrays. One is here, this one. First one will be one subarray with elements less than pivot. This one, elements, I can write in this, right? So here, sorry, this has to be elements less than pivot. And the second one will be, the second subarray will be, another will be elements greater than the pivot. So I can simply write here elements greater than the pivot. So this is the thing. So it will select the pivot element from the array, and it will partition the other elements into two subarrays. So one subarray will be elements that is less than the pivot, and another subarray will be, it will be another with elements greater than the pivot. So the process is recursively repeated for the subarrays. So next step is, the process is repeated recursively repeated for the subarrays. So we'll be making use of the recursion again here. The process will be recursively repeated for the subarrays. So what will be the base case then here? The base case of the recursion here occurs when the size of the subarray is either 0 or 1. Let's consider the base case here. Base case is when we have the element 0, only 0 elements in the array, I mean with no elements in the array, or either when we have only one element, meaning that it is already sorted. If we are having 0 elements, then it is, we can consider this one is this one as already sorted, and if we are having one element, then also we can consider this one as already sorted. So let's come to the last step. So it has average time complexity of big of n log n, right? So, but in the worst case, when I say worst case, means when the pivot is dividing the array into unbalanced partitions, then it can degrade it to big of n square. At worst, this will be having big of n square, and normally this will be big of n log n. So let's discuss the time complexity and the space complexity at the end. So here, this will be the, basically, this is the approach to the algorithm. So let's write the code and try to understand, right? So in a better way. So I'll just come here. Let me give function. Let me consider this one, quick sort. Array of elements, ARR I'll consider. Low, I'll consider 0 initially. High, I'll consider length of the array minus 1, nothing but the last element. So this one will be length of the array minus 1, last element. So let's go with the base case first. If the lower index is less than the upper index, nothing but I can write in this way. If low less than high, then we will partition the array and get the partition index, nothing but it is pivot's final position, right? So I can write in this way. I'll just take this one, pi, and for the partition, so what I'll do, here we have not yet written the partition, this one yet, right? So we'll be writing that one in the future. So let me write this now itself. While writing the partition, this one function, I'll explain this one clearly. So we will partition the array and get the, so let me do one thing. Let me leave space here. So we will recursively apply quicksort to, we have to recursively apply the quicksort to the left subarray and the right subarray. This is after applying the partition, right? So first, initially, let's write the partition. Then let's try to understand this one with the further steps. So just give me a second here. So I'll just come here. So this has to be function. I'll just take partition here. Within the partition, we'll take 3 parameters. One is array, low, high. So let's select the pivot element, nothing but the last element in the current subarray. I can just write in this way. Const now, or let pivot equals array of high. We are considering the highest element, right? This will be the pivot element in the current subarray. So next, let's initialize the index of the smallest element, smaller element, nothing but just before the first element, right? I can just give low minus 1 here. I'll just take some random variable. I'll just take I equals low minus 1. So next, let's loop through the each element of the array from low to high minus 1. Nothing but from low to high minus 1 is nothing but starting element to the last element, right? So I can write in this order. So let's say equals low, j less than high, and j plus plus. So here, if array of j, if it is less than pivot, then what we will do, we will just move the I pointer to the next position where the smallest smaller elements go. So I'll just increment the I here. This one is easy. Next, let's swap the current element array of j with the element at the index I. So I can clearly write in this way, right? So within the array of I and array of j, we are swapping here. So this one, array of j, this has to be equal to within the array of j and array of I. So this has to be array of I. So I hope this is clear. So finally, what we will do here, after the loop, we will swap the pivot element with the element at the index I plus 1. So after the loop, we'll be swapping the pivot element with the element at the index I plus 1, nothing but next element. So this will put the pivot in its final sorted position. So I'll just write this one. You'll clearly understand when I write the code. Here, this one, I plus 1 and array of I. This has to be, this is equal to, they are just swapping here, right? This will be array of I and array of I plus 1. Oh, this has to be I plus 1. That's it. I hope this is clear. Finally, after this step, we will be returning I plus 1. So I hope this is clear. So now we have the partition function. We will come to the quicksort function, and then here we will write whatever that is needed. So after this, base case was if the lower index is lesser than the upper index, then what we will do, we will partition the array and we will get the partition index, nothing but pivot's final position. So here you can now you clearly know the partition function, right? Now we can just partition the array and get the partition index. So I'll just write here partition of, so what are all the parameters that we have? Array, low and high, right? So yeah, I'll just consider array, low and high here. Next, as usual, we had discussed this one in the approach as well. We will recursively apply quicksort to the left subarray as well as the right subarray. Left subarray, when we are recursively applying the quicksort to the left subarray, this will be before the pivot. And when we are recursively applying the quicksort to the right subarray, this will be after the pivot. I'll just give here quicksort of array low as well as high. So this is fine. Next, again, quicksort of array
And that's the plan.
pi plus 1, and finally this will be high. So finally what I'll do after this step, so why this is m quicksort? This is just a quicksort. So here did I type m quicksort? So just make this one quicksort. Finally what I'll do, let's return the sorted array. Final output, this will be in the ARR, right? So I have considered ARR itself array. Yeah. So finally we will be returning the sorted array, nothing but the final output. So I hope this works. Let's see the example usage, and then we will be discussing the time complexity and the space complexity. So just give me a second here. So I'll just give here example usage. So I'll just consider here directly. For example, let me consider some array. I'll just take 7, 8, 9, 1, 5, some random array I'm considering. So I'll just go with the console log of original array, and this has to be array. So array we are considering main array, and we have to get the sorted array, right? We'll be making use of the quicksort function here of array. So I'll just let me make use of the console log of this one here. Let me give this one clearly sorted array, and finally sorry, not this one, ARR, small a, right? Why this is not taken? Okay, smaller. So let me hit the run button. So here what happened? Unexpected identifier. Consider what happened. See, I have gaps here. So let me run this one again. What happened here? Why? Missing. What have I missed here? Just give me a second here. Array, I have initialized this one correctly. This one is fine. Console log of original array. And here, yeah, on this one, let me give comma here. So let me run this one again. Yeah, maximum call stack. 10, 7, 8, 9, 1, 5 we are getting. So here range error maximum call stack exceeded by. Let's check. So what mistake I have done here is, here in the recursive function that I have used here, right? The recursive call, I have made the mistake. So I have confused with this one, I think, partition. So this has to be quicksort. While typing I did wrong. Here, but this has to be array low as well as I considered pi, right? It has to be pi minus 1, right? So this is for, we are recursively applying the quicksort to the left subarray, this one. We are recursively applying the quicksort to the right subarray, this one, second one. So now this has to work. Let's see. Let me hit the run. Yeah. Now you can clearly see the original array was 10, 7, 8, 9, 1, 5. So we are getting the sorted array 1, 5, 7, 8, 9, 10. So we are getting the correct answer, right? Correct solution. So this is in the ascending order. So you can check for the descending order as well. So yeah, this mistake that I had done while making the recursive call, I did make a mistake, and also here I missed the comma, right? So this is fine. I hope this is the quicksort is clear. So this is it. Thanks for watching, guys.